Let's begin today with the video. This is going to be the third video for the class, focusing on, again, on this notion of using Magic Wand, but now in the context of chemical equations. So we're going to be able to convert between reactants and products using that idea of a Magic Wand. And also, one of the things I want to explain to you today is the way in which a chemical equation is equivalent to a mathematical equation. So this is all material that we're going to use for Monday, the first Monday of the semester. We want to get into the notion of chemical equations, and as you've read in your textbook and as you're probably familiar, in chemistry, when a chemical reaction occurs, atoms are not destroyed or created. We have the same number of atoms at the beginning of our reaction, and at the end of the reaction, all that happens in a chemical reaction is that partners change. And so when we write a chemical equation and balance it, what we're doing is keeping track, making sure that we have the same number of atoms at the beginning and at the end. So I'm going to give you an example today. We're going to balance a chemical equation together. We're going to talk about the equivalence between a chemical equation and a mathematical equation. And then we're going to use that idea of a Magic Wand, which I introduced in the last video, to convert between number of moles of reactants and products or number of moles of reactants. So let's try that today with an example of the combustion of methane. And as I've made clear earlier in the semester, we have this focus on energy this semester, and so the examples that I use are examples that I expect you to pay attention to. I'm not just randomly throwing out some A plus B equals C. These are reactions that are really important in thinking about energy. And methane is the primary component of natural gas, and so when that combusts, that reacts with oxygen to form carbon dioxide and water. So that's a standard combustion reaction. And now to balance it, and you'll have a lot of opportunity to practice this, but what we have to do is we have to make sure we have the same number of atoms on the reactant side as we do on the product side. And there are some tricks to doing this. It's also something you're just going to practice. But let's go through this systematically and watch how I do it. So first I'm going to look at carbon, and I have one carbon here and one carbon here. So my equation is already balanced with respect to carbon. So for now, I'll leave those alone. It turns out that it's often easiest to balance oxygen last, so I'm going to leave that alone. I'm going to go next to hydrogens. I have 4 hydrogens here and only 2 hydrogens here. So if I put a coefficient of a 2 in front of the waters, I have 4 hydrogens and 4 hydrogens. So at this point, I'm balanced with respect to carbons and hydrogens. Let's look at oxygen. So I have 2 oxygens here. I have 4 oxygens on this side. So if I simply multiply the number of molecular oxygens by 2, I should be balanced. But I'm always going to take a moment and check my balancing because I'm always going to do that. It's easy to make a mistake. So again, 1 carbon, 1 carbon, 4 hydrogens, 4 hydrogens, 4 oxygens, 2 plus 2, 4 oxygens. Yep, I have a balanced equation. So that's great. That's the starting point for almost anything that we're going to do in chemistry, and that's going to be true throughout your career in chemistry. So a balanced equation, a balanced chemical equation, in a chemical terms, what we're saying is that 1 mole of methane plus 2 moles of oxygen reacts, combusts to form 1 mole of carbon dioxide and 2 moles of water. But we can also think about this in mathematical terms, and we really can rewrite this and say that 1 mole of methane plus 2 moles of oxygen is equal to 1 mole of carbon dioxide and 2 moles of water. That arrow really represents an equal sign in mathematical terms. And so what that then allows me to do is to make magic wands that I could use to convert between moles of reactants and moles of products. So for example, if I have 1 mole of methane, and I have all the oxygen in the world that I need, how many moles of water can I make? That's the question. And so this is fairly straightforward in this problem, but I want to show you that I can answer that question by using the magic 1, by recognizing that 1 methane equals 2 waters. So just as I did in the previous video, I can set up a magic 1 in which, let's say, I think I'll do it this way, 2 waters is equal to 1 methane. This represents, again, that magic 1 that we were working on in the last video. And so now, if I say, well, if I have 1 mole of methane, how many waters can I make? I can treat this mathematically, just like we did in the problems before. I can say 1 mole of methane. And now I multiply that by my magic 1. And just like we did in the last set of problems where we would cancel grams or cancel moles, I can actually cancel methanes and treat that mathematically. And then I'm left with 1 times 2. I'm left at the end with 2 moles of water. So that's my answer, that if I have 1 mole of methane and I have all the oxygen I need, I can make 2 moles of water. That might seem obvious because that is what the balanced equation said, but I'm going to show you in a minute that writing this equation explicitly in terms of this equation between equivalent moles of methane and water, and equivalent in this case is the equivalence that is defined by our balanced chemical equation, recognizing how it has a mathematical analogy, gives us an answer. And in the moment we do a slightly more difficult problem, you'll see that using that magic 1 simplifies a lot of problems. So let's continue now with a slightly less obvious example. But again, the fundamental idea here is that we can treat this chemical equation as a mathematical equation, write magic 1s that allow us to relate the ratio of reactants to products, and then use that magic 1 to easily convert between amount of reactants and amount of products. So the last example seemed relatively straightforward, just giving the balanced equation. But what if I have only 1 mole of oxygen? Then how many moles of water can I make? So let's again set this up. What is the magic 1 that relates oxygen and water? From the balanced equation, we can see that there are 2 moles of oxygen to 2 moles of water. So that's directly from our balanced equation. So for the relationship between oxygen and water, this is our magic 1. So now if we have 1 mole of oxygen, moles of oxygen will cancel, and we'll be left with 1 mole of water. So that's maybe a little less obvious. Given 1 mole of oxygen, multiplying by the magic 1 that relates oxygen and water, we find out that we can make 1 mole of water. And we can use this same approach then to think about the relationship between reactants. So if I have 1 mole of oxygen, how many moles of methane will I use in order to use up all of the methane? So it's the same, all of the oxygen. So we have 1 mole of oxygen, and now again we write our magic 1. In this case, the magic 1 that relates oxygen and methane, and we see that there are 2 moles of oxygen for 1 mole of methane. This again is our magic 1 that relates oxygen and methane. oxygen moles of oxygen will cancel, and we'll be left with moles of methane. So in a very straightforward fashion, what all of this just told us is that if I have 1 mole of oxygen, I can make 1 mole of water, and if I have 1 mole of methane, I will consume only 0.5 moles of methane. So this sets you up for something we're going to work on in more detail in the next class, which are limiting reagent problems, where you don't have enough of both of your reactants to make all of the products that you want. And these are problems that chemistry students traditionally find a little challenging. But by sticking with this magic 1 that comes directly from the balanced chemical equation, thinking about the balanced chemical equation in mathematical terms, I promise you, you will come to love limiting reagent problems. So we'll go away and practice a few of those, and we'll come back and see how they're going. Okay?